start looking at some calculations. I'm going to show you 4 different types of calculations you may see, just to give you a general idea how to solve these things. First of all, calculate the molarity. Alright, so that's what I'm looking for. I'm looking for molarity. And as I said before, it's moles over the liters. Okay, so you've got to remember that it's liters on the bottom. So we're going to calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous HCl. Doesn't matter that it's gaseous, don't worry about that part. What we're more concerned is that I have a mass of solute. In this case, my HCl is the solute. So I have 1.56 grams of HCl that I'm putting in solution. And enough to make a solution, or make, enough water is added to make 26.8 milliliters of solution. So what I have here is I do have the volume of solution. So I'm good here. I don't have to worry about any addition or adding solute to solvent because I know that I have 26.8 milliliters of solution. Watch your units. I said before this should be in liters. So I'm going to go ahead and right away make that conversion and convert that to 0.0268 liters. You should know how to convert milliliters to liters at this point. Alright, so it's pretty straightforward. All I need to do is I need to find my moles and my volume. If I'm going to solve for molarity, it's always about moles per liter. So what I'm going to do is I'm going to use this and convert my grams to my moles, which we've been doing pretty much all year long. 1 mole is 36.46 grams of HCl. Alright, so when I do this calculation, I end up with a number of moles equal to 0.04 279. I'm going to keep more significant figures than I need for HCl. And now I have moles and I have liters, so I'm going to find my molarity. So I just take my moles over volume. So 0.04279 moles of HCl over my total volume of solution, which is 0.0268 liters. And when I do that, I end up with 1.60 molar. Okay, and that would be my final answer. I rounded that to significant figures because I need to have 1, 2, 3, 1, 2, 3, 3 significant figures, my final answer. So I did that, and I need to keep the 0 there. Now, if you want to, you can call this 1.60 moles per liter. That's fine too, because that is the same unit for molarity. So either unit is fine. Notice that these do not cancel out, but if you want to write the capital M, you can, or if you want to write moles per liter, that's acceptable as well. Okay? So let's go ahead and take a look at another example. In this case, we're looking at finding the moles of ammonium nitrate. I'm sorry, not ammonium nitrate, just ammonia. So we have ammonia here, and we have 35 milliliters of solution and 1 molar solution here. So what I'm looking for are my moles. How many moles of ammonia do I have? Let me stop this for a second. Okay, so looking for moles of ammonia, I know that the volume is equal to 35.0 milliliters, and my molarity is equal to 1.3 molar. Okay, as I said before, I would strongly recommend that you convert this right away to moles per liter so that you remember what that capital M represents. So in this case, I'm looking for the number of moles. Okay, so I'm looking for moles here, and I have the volume. Now, if you remember before, in the intro lesson here, I talked about the fact that if you have molarity and you have moles over the volume, if you want to solve for your number of moles, it's the volume times your molarity, right? You're going to multiply these two together to solve for the N. So all I need to do is take my volume and my molarity and multiply those two together. Every time I see volume and molarities, I can find my number of moles. This little statement right here is telling me the number of moles. So I take my volume, 35, well actually, nope, remember units, I got to make those units, I got to fix that. So I don't want 35, I want 0.0350 liters. Okay, so what I'm going to do is then use this as a conversion factor. I'm going to put my liters on the bottom because I want to find the moles. So liters go on the bottom. In this case, it's always 1 liter by definition and 1.3 moles of the ammonia in there. So that's the whole point, is that 1.3 moles for every 1 liter. I don't have a liter, so how many moles do I actually have? Well, in order to figure that out, I multiply these two together, and I end up with 0.0455 moles, and in this case my problem should be rounded to two significant figures based on the 1.3, so 0.046 moles of NH3 are required. Okay, so we can find moles, we can find the molarity, and let's take a look at what happens if we have ionic compounds. So if you remember, we talked about ionic compounds. When we see cobalt nitrate, when we see ionic substances dissolved in water, we have to right away think about them as dissolved, right? So I have one cobalt ion with a positive 2 charge, and I have twice as many moles of the nitrate. My iron chloride, I have a 3 plus charge on that iron, and I also have 3 chloride ions. So therefore, when I'm looking at the concentration here, these concentrations are going to be concentrations for the iron are going to be the same, while this one is going to be 3 times the amount. So if we think about the equation, moles per volume, when we deal with these equations, these are called dissociation equations. If I have 1 mole of cobalt nitrate, I have 1 mole of this, and then I have 2 moles of the nitrate. So if I'm looking at just the concentration, remember the brackets mean concentration, so I'm looking for concentration of cobalt-2. I'm looking for the molarity. Remember, brackets mean concentration. Well, if I know that this is 0.50 moles for every 1 liter, and this is for the cobalt nitrate, well, cobalt is going to be the same. So therefore, it's going to stay 0.50 molar cobalt. No change. All right. For the nitrate, things are going to be a little bit different now, right? If I look at the nitrate, I'm going to start with that 0.5, but I have to, my moles are double. The number on the top here is actually doubling, so this multiplies by 2 because I have twice as many ions in solution. So therefore, my concentration here is going to be 1.0 molar for my NO3 minus. Okay? Now, if I'm looking at iron and chlorine, I got to remember that the chloride has a 3 in front of it. So for my iron, it's going to be the same because there's no change because it's a 1-to-1 ratio between iron chloride and the iron. So therefore that stays at 2.5 molar, while my chloride ion actually goes and triples. So therefore I would have 7.5 molar chloride. I'm going to go 3 times the amount of whatever the iron ion is. Okay? So keep in mind that when we deal with ionic compounds, we don't really think about them here. We think about them as ions in solution floating around. All right, last problem. This would be how we create solutions. So if I want to analyze alcohol in a certain wine, I'm going to need 150 milliliters of a 0.2 molar potassium dichromate solution. Question is, what mass of that potassium dichromate do I need? Okay, so that's what I'm looking for here. That's my goal, is to find this mass. Well, I know what the volume is. I know it's 150 milliliters, and I know that my molarity is equal to 0.200 molar. Remember, that's moles per liter. Well, if I'm looking for the mass, hopefully remember that you probably want to find moles somewhere, right? Well, here's our moles right here. Whoops. Here's the moles that we have. It's at the top here. Okay, so what I'm going to do is I'm going to go ahead and get rid of my milliliters. I'm going to go ahead and convert that right away from milliliters to liters. 1 liter is 1,000 of these, so therefore I move it over and it's 0.150 liters. So my goal here is to find the moles. So I saw earlier that if I multiply volume and molarity, I can find the moles. So moles are equal to 0.150 liters multiplied by 0.200 moles over my liters, 1 liter. I do that calculation, I can figure out that I have 0.0300 moles of the potassium dichromate. Okay. Now what I do here is I just take that potassium dichromate number of moles and I convert that to mass. So I use my molar mass. So I put down here moles and I put my grams, and it's nice. I gave you that in the problem, so 294.2 for every 1 mole. I do that calculation and I end up with 8.826 grams, which again, rounding to significant figures, I have 3, I have 3, I have 4, I'm going to go to 3, so 8.83 grams of potassium dichromate. Okay, so there's a variety of problems there for you. So if you want to take a look at that, practice, that'd be great. And I'll see you guys in class. Bye.